make more specification, makes them more complex in order to test more complex protocol, then we require more specification, and then it's becoming a tedious job. So also, like, fuzzers are generally stuck with a quantity of modification that you can do in the package. So after we finish this set of modifications, then we cannot test anything else because the tests are finished, and that's it. So also, when we are generating the messages, we don't know if like how it will be the crafted message that we'll send to the entity. And if we don't know that, it will be even harder to know which could be the estimated answer from the target entity. So we have to see if we'll send a message, if the message will be complying with the grammar, it will not. We have to dig in those aspects. So also, okay, most fuzzers, they just test if they success only based on if the target device crash or not. And as Radu will show some examples, most of the vulnerabilities found were because they were doing action that they weren't supposed at any moment, but the devices didn't crash at all. And learning is not considering from previous examples, from previous traces, and we don't know when to stop a test. Like we can use a time measure, like quantity of tests, etc. So, okay, we can split fuzzing into in syntax and stateful. We know that if we send a message, an invalid message, then we can reveal some vulnerabilities. For that case, we have to think if which fields of the message we will modify in order to send it, for which values we will replace it, and if we want the output message to be complying with the grammar or not. And in the stateful part, we know that an unexpected message can also reveal a vulnerability. For example, the grand string font that we send a 183 ring session in progress, and then the phone starts to send RTP data. So we have to decide what type of message to send and what time moment to send it. Now, in syntax fuzzing, we can classify it in 3 different categories. So we have, first of all, well, okay, nothing is working today. Oh, there you go. So we have, first of all, the random fuzzers that they are the easiest one to launch. You don't need knowledge about the protocol that you are fuzzing. They just see the message as a sequence of bits where you just can flip the bytes and see how the entity responds. So as soon as we move to more complex protocol, we can realize that those fuzzers are not really useful. Then we have the block-based fuzzers, which they have knowledge about they might have knowledge about the protocol, and they see the message as they divide the message in sections or blocks, where those blocks we can modify and put different values, and those values can be generated from a set of, we can obtain it from a file or from a database, wherever. So as soon as we have to make the specification for such a fuzzers, we realize that it's a tedious job and nobody wants to do it. And finally, we have the grammar-based fuzzer that they base the message is based on the grammar of the protocol. We can say that the grammar fuzzers are kind of a fine-grained block-based, and also, when you want to make a specification of such a fuzzers, then you have to provide the grammar, and that is usually tedious. So in our approach, we use actually the grammar-based fuzzer, but in order to make it easier, what we do, we know that all protocol or specifications, they provide a syntax grammar. in the RFC, for example, and those syntax are in AVNF way. So we can, like that syntax explain every field of the message. So we can reuse that syntax and create our fuzzer. So the general the overview is like that. We have, first of all, AVNF grammar. For example, here we take the zip grammar. We use our library. We create some intermediary modules. One is a zip parser, and the other a zip fuzzer. So whenever we interact with a phone, the phone will send us a message. We'll be able to parse the message because we have the whole syntax, so we can know when the message is valid or not. And then we can, when we extract that information, we can use our stateful engine. And when we decide to send a new message, we will call the syntax fuzzer, where we will give one scenario to tell him how to behave, how aggressive or not to behave. And okay, once the message is generated, we send it back to the phone, and then we see what happened. So, okay, more in detail, how is this grammar-based fuzzer? First of all, we have a AVNF grammar. Here, for this presentation, we made up a really simple one. And we have a message that is complying with that grammar. So this tree will be the tree representation of the message based on the grammar. So the leaves of the tree will be, in fact, the message itself. And each node of the tree will represent one section of the message. So if we take the root of the tree, is the whole message. If we go to one of the branches, then we have just like some part, like for example the first part of the message, and so on. So okay, why we use such a complex structure? What we gain from all that? First of all, we have the syntax of the whole message, and specifically of each field of the message. So we can generate any part of the message from scratch. So that could be the whole message, could be an IP address, could be username, could be a header, could be wherever. So the idea is we generate such a message, and if we have a tree representation of a message, then we can replace some branch of the tree, and in that way we are mutating a message, or we are merging several messages. Also, in order to create such branches, we can use statistics learned from previous traces, previous examples. So, for example, here we know that the entity, the field's entity, usually have a value as root, like 50 times of the 50% of the time, or 30% of the time we have user values. So we can use those statistics to generate new branches. And we generate a branch, and then we replace it on the tree. And also we can evolve the rules. So in order to understand how it's working, well, actually it's easy. So we have for example, the message, message.one rule. It was a sequence, a repetition of spaces. So we can evolve that rule to be a repetition of spaces and string formats, where we can define on the fly such a rule, string formatters, and then we can start we get the result that starting from the replay user version blah 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 blah, we get the new version. Sorry, we get the new message that is request, root, etc. with the string formats, etc. So we can use those rules to make mutation, make messages from scratch, etc. So okay, I'm doing fine with that. So okay, so the syntax model is totally general to any protocol. The only thing that it needs is just a AVNF grammar as input. Now I will move to what is KIF, the tool that we developed. And this tool is related to zip, because we have a stateful engine that we need to keep track of all the state of the phone. So the KIF is divided in two main components. First, the syntax fuzzer, that is the one that I explained, and the state protocol fuzzer, that is the one that I will explain in the following. So whenever we receive a message from the phone, we'll parse it, we'll get the tree representation, and we'll give it to the stateful